Section: Introduction. We're going to talk about a new approach to solving math problems using machine learning. The current best methods use something called Supervised Fine-Tuning, SFT, and chain of thought, COT, annotations. Think of COT annotations as a roadmap of the steps needed to solve a math problem. Usually, there's one COT annotation for each question in the training data, which is used in SFT. However, we've noticed that this can limit the model's ability to generalize, as there can often be multiple valid COT annotations for the same question. To tackle this issue, we've come up with a new method called Reinforced Fine-Tuning, ReFT. This method starts with a warm-up stage of SFT for 1 or 2 cycles. This initial stage gives the model a basic ability to generate correct answers to math problems, as shown in previous studies. After this, ReFT uses an online reinforcement learning (RL) algorithm, specifically proximal policy optimization (PPO), to further refine the model. This allows ReFT to sample multiple correct reasoning paths or COT annotations and learn from them. Since the training data includes the correct answers, we can use these to reward the model when it gets the right answer during PPO training. This means we don't need a separate reward model. In contrast, another method called RLHF does need a reward model that is learned from human-labeled data. During the warm-up stage, ReFT achieves a certain level of accuracy through supervised learning. In the RL stage, ReFT further improves its ability by learning from various COT reasoning paths. This gives ReFT a much richer set of signals to learn from than SFT, which allows it to greatly improve its ability to solve math problems. We've found that ReFT performs better than SFT using the same training questions, without needing any extra or augmented training questions. In fact, ReFT can be easily combined with such data engineering. Our main contributions are as follows. 1. We've introduced a new fine-tuning approach, ReFT, which uses reinforcement learning to solve math problems. ReFT shows better generalization abilities than the traditional SFT when trained on the same dataset. 2. We've carried out extensive experiments using 2 foundational models, Code-L-Llama and Galactica, on 3 standard mathematical datasets, GSM-8K, MathQA, and SVAMP. Our experiments cover both natural language and program-based COTs, showing the significantly improved performance and generalization ability of ReFT. 3. We've also shown that ReFT benefits from both majority voting and reward model re-ranking at inference time, which further improves its performance. In terms of related work, recent research has focused on COT prompt design and data engineering. Some have tried to make COT more comprehensive and detailed to show the step-by-step reasoning solutions. Others have proposed using Python programs as COT prompts, which provide more accurate reasoning steps and significant improvements over natural language COT. Our work is mostly related to recent work that applies PPO to natural language processing for aligning human preferences. Since then, several training algorithms have been proposed to efficiently improve the alignment. Other than alignment, we aim to use reinforcement learning as a fine-tuning paradigm to improve performance over conventional supervised fine-tuning. In this work, we focus on natural language COT, NCOT, and program-based COT, PCOT, using Python. We use the terms NCOT and PCOT to represent natural language and program-based COTs in the rest of this paper, respectively. Section Summary. The state-of-the-art approach to solving math problems involves supervised fine-tuning, SFT, using chain of thought, COT, annotations. However, relying on a single COT annotation for each question limits the generalization abilities of the models. To address this, we propose reinforced fine-tuning, ReFT, which combines SFT with online reinforcement learning, RL, using proximal policy optimization, PPO. ReFT samples multiple correct reasoning paths and learns from them, resulting in improved generalization and performance in math problem solving without the need for extra training questions. Section: Reinforced Fine-Tuning. Our proposed method, Reinforced Fine-Tuning, ReFT, is a 2-step process. It begins with a warm-up stage, followed by a reinforcement learning stage, In the warm-up stage, we fine-tune the policy for a few rounds using a dataset made up of question and COT pairs. This helps the model develop basic problem-solving skills, enabling it to generate appropriate responses to questions. The COT generation process can be broken down into a series of actions predicting the next token. The process ends when the last action token, less than EOS greater than, is produced. The COT is represented as a sequence of actions, ending with the less than EOS greater than token. The maximum length of this sequence is denoted by L. At each step, an action is chosen based on the policy, which can be any token in the vocabulary. The state at this point includes all tokens in the question and all tokens generated up to this point. After each action, the resulting state is a combination of the current state and the action. When the action corresponds to the less than EOS greater than token, the generation process ends. In the reinforcement learning stage, the policy improves its performance through a form of self-learning. This is done using a dataset made up of question and answer pairs. The policy model learns by repeatedly sampling responses, evaluating the correctness of the response's answer, and updating its parameters. We use the proximal policy optimization (PPO) algorithm with a clipped objective for training. The reward function gives a score of 0 for all actions resulting in non-terminal states. At the terminal state, the reward function compares the answer extracted from the state's COT and the actual answer. If the answer is correct, the reward function returns 1. Otherwise, it returns 0. On datasets where all answers are numeric, a partial reward of 0.1 can be given when the answer can be extracted and is of numeric type. This partial reward can help reduce the impact of learning from sparse rewards. Our total reward is the sum of the reward function score and the Kullback-Leibler (KL) divergence between the learned RL policy and initial policy, scaled by a coefficient factor. We use the generalized advantage estimate for advantage calculation. The temporal difference, TD, is defined as the difference between the reward and the value of the current and next state, discounted by a factor. The estimate of return is the sum of the generalized advantage estimate and the value estimate. The policy and value objectives are represented by two equations. The unified loss function is the weighted sum of these objectives. We tested our method on 3 math problem datasets: GSM-8K, SVAMP, and MathQA. For GSM-8K and SVAMP, the answers are numeric values, while in MathQA, the answers are multiple choice options. We used GPT 3.5 Turbo to obtain both the NCOT and PCOT annotations. We also conducted an additional experiment on a numeric version of MathQA to demonstrate our assumptions of potential reward hacking phenomenon on MathQA. Section summary. The reinforced fine-tuning (ReFT) process consists of 2 stages: warm-up and reinforcement learning. In the warm-up stage, the model is fine-tuned on a dataset of question and COT tuples to generate proper responses. In the reinforcement learning stage, the policy model improves its performance by sampling responses, evaluating their correctness, and updating its parameters using a reward function and the PPO algorithm. Section Baseline. We're comparing our method, ReFT, with 2 other methods, SFT and self-training. SFT is a simple method that fine-tunes the language model using the training data. Self-training methods are a good comparison because they all use samples generated from the model for training. We use 2 types of self-training: offline self-training, offline street, and online self-training, online street. Offline ST is similar to expert iteration. We first use an early SFT checkpoint to sample the COTs and check them against the real answers. We only keep the expert samples that are correct. Then, we fine-tune the model using both the original training data and these expert samples. Online ST is designed to be similar to ReFT. Like ReFT, online ST has a warm-up process. After that, we continually train with samples generated in real time. At each training step, the model first samples COTs for a batch and only keeps the ones with correct answers. The resulting batch is a mix of sampled and real COTs. We then update the model parameters on this batch using the SFT objective. Unlike ReFT, online ST doesn't use negative responses, ones with incorrect answers, and doesn't have a specific mechanism to stop the model from diverging too much from the initial model, which can lead to overfitting and instability in training. We conducted experiments with two foundation models, Galactica 6.7b and Cadellama 7b. These models are known for their strong performance in solving math problems and are often used in recent literature on reasoning tasks. We also applied common techniques, majority voting and reward model re-ranking on GSM-8K. In all experiments, we trained the models using 8 A100-80 GB GPUs with Deep Speed 0 Stage 2 and Hugging Face Accelerate. During the warm-up stage of ReFT, we used the Atom W optimizer with a warm-up ratio of 0.1. The batch size was set to 48 and the learning rate was 0.00001. The maximum length was set to 1024. The number of warm-up epochs was either 1 or 2 in all settings except on MathQA MCQ and MathQA Numeric, where we used up to 5 and 10 respectively. The model was trained for 300 epochs with a learning rate of 0.0000003. The parameters lambda, gamma, alpha, epsilon, and u in PPO were set to 1, 0.95, 5, 0.2, and 2, respectively. The KL coefficient beta was set to 0.01 for PCOT and 0.05 for NCOT experiments. We also trained a reward model, ERM, to determine the correctness of the COT. To create the ERM training data, we used the model from the warm-up stage and sampled 100 COTs for each question in the training set. The COTs were deduplicated and the binary labels were obtained by comparing the extracted answer against the real answer. The reward model is a language model that is initialized from the best SFT checkpoint. It's trained to predict a binary label that indicates the correct or incorrect solution. The solution with the highest correct score among the candidates is selected as the final answer. We trained the ERM model for 3 epochs using a batch size of 48 and maximum length of 700. We reported value accuracy for both NCOT and PCOT on all datasets. Specifically for majority voting and re-ranking, we sampled 100 COTs for evaluation. In voting, the valid answer with the most counts is chosen as the final answer for computing accuracy. In re-ranking, we choose the COT with the highest score and extract the answer. Section Summary. The section compares ReFT with SFT and self-training baselines, where SFT fine-tunes the language model on the training data. Offline ST and online ST are implemented as self-training methods, with offline ST similar to expert iteration and online ST closely comparable to ReFT. The experimental setup involves using GALACTICA 6.7b and CODELLAMA 7b foundation models, and hyperparameters are specified for ReFT, SFT, offline ST, and online street. Reward model re-ranking is performed using a reward model to determine the correctness of the COT, and evaluation is done by reporting value accuracy for both NCOT and PCOT on all datasets. Section. ReFT outperforms SFT. Our research shows that our proposed method, ReFT, consistently outperforms the standard fine-tuning, SFT, and other self-training approaches across various datasets, including GSM-8K, SVAMP, and MathQA. The only exception was the MathQA multiple choice question, MCQ, NCOT. In particular, we saw a significant improvement of over 9 points and 8 points respectively when using code LLAMA on the GSM-8K NCOT and PCOT datasets. On average, we saw an improvement of 3.7 points and 5.9 points across all datasets in NCOT and PCOT respectively. What's more, ReFT achieved these results without the need for additional annotations or reward models. This demonstrates the robustness of ReFT and its potential for further exploration of training data using reinforcement learning. We also found that offline self-training, which involves sampling data from the initial policy for fine-tuning, can sometimes improve performance compared to SFT. However, the improvements were not as significant as those achieved by ReFT. This suggests that exploration is a key factor in achieving good performance with ReFT. We also compared ReFT with online self-training and found that while there were some improvements with Galactica, it still lagged behind ReFT on average. This suggests that incorrect instances are crucial for guiding the model towards better exploration. Our research also revealed that ReFT struggled with reward hacking during training on the MathQA MCQ. This was due to the model receiving positive rewards for incorrect answers, which misled the model and negatively impacted training. To mitigate this, we chose a checkpoint with longer warm-up steps for MathQA. We also experimented with a variant of MathQA _numeric, which removed the options in the question and required the model to predict the numeric answer directly. The results showed that ReFT consistently outperformed SFT using both Galactica and Code Llama. We also found that ReFT benefited from common techniques such as majority voting and reward model re-ranking. In fact, ReFT plus voting significantly outperformed SFT plus voting by an average of 9.2 points across all settings. We also conducted experiments with a small language model, Galactica 125M, and found that ReFT still outperformed SFT on 3 datasets, demonstrating its robustness. Finally, we performed an ablation study using Code Llama on the GSM-8KP COT dataset. Without the partial reward, ReFT still achieved a higher accuracy than SFT, but it was lower than when the partial reward was included. This suggests that the partial reward can help reduce the effect of sparse reward during training. In conclusion, our research shows that ReFT is a robust and effective method for improving performance across various datasets and settings. Section Summary. The proposed ReFT approach consistently outperforms the SFT and self-training methods on various datasets, achieving significant improvements in performance without the need for additional annotations or reward models. The comparison with self-training approaches also highlights the superiority of ReFTs on policy sampling and reinforcement learning over standard data augmentation methods. However, ReFT faces challenges with reward hacking in MathQA, where inaccurate rewards misguide the model during training. Despite this, ReFT still outperforms SFT on MathQA variants and benefits from majority voting and reward model re-ranking techniques. Additionally, ReFT demonstrates robustness even with smaller language models, and partial rewards help mitigate the effect of sparse rewards during training. Section: Generalization. In simpler terms, the diagram illustrates the average reward, evaluation accuracy, and the KL divergence during the training of ReFT on GSM-8KP COT. SFT reaches its peak and starts to overfit around the 40th training cycle. However, the average reward for the ReFT policy is between 80% and 90% at the 40th cycle, and the accuracy of the value is also on the rise. Moreover, the KL divergence, as shown in Figure C, is initially quite high but then settles to a reasonable value between 0 and 10. This stable KL divergence suggests that our policy is exploring within a space that contains suitable programs. The underlying reinforcement learning mechanism significantly enhances the generalization ability of ReFT. Now, let's delve into when ReFT outperforms SFT. To better understand the relationship between ReFT and SFT, we trained ReFT with varying numbers of warm-up steps from SFT. The diagram shows the value accuracy of different ReFT versions compared to SFT. Specifically, if the warm-up step is 3, this means the policy starts from the checkpoint of the 3rd training cycle of SFT. Initially, all ReFT policies perform worse when the training cycle is less than 8. This is because the linear layer in the shared value model is randomly initialized and it may take a few cycles to adjust the distribution. However, starting from the 30th cycle, SFT reaches its peak while all ReFT versions continue to improve. We also observe that all versions of ReFT significantly outperform SFT, and there is no clear advantage of any specific ReFT version.